Okay, this lesson is on 7.1, slope fields and anti-differentiation. As you can see from the notes here, most of the formulas we already have. This is just a kind of a good reminder of, hey, these are your integrals and they are derived from these derivatives that you knew from in Calc A, specifically in chapters 3, 4, and 5. One thing to remind you of is, of course, the power rule right here, where we are adding 1 to the power and dividing by the new power. Second thing would be this piece of the 1 over x. So if you have x to a single power on the bottom, your antiderivative will be a natural log. All right. New thing, or kind of a reminder of something, is that when you have e to the x, the integral of e to the x is still e to the x, just like the derivative of e to the x is still e to the x. But we got to keep in mind the chain rules. So if you have a coefficient in front of your x, what is it going to do now? It is going to come out as a reciprocal. So this coefficient comes out as a reciprocal when you take an antiderivative. Same thing with your trig functions. If you have a coefficient in front of your x's, here in sine and cosine, as an antiderivative, it's going to come out as a reciprocal. It's going to go down on the bottom like so. Okay, so just kind of a reminder of some things like this. Okay, so let's take a look at a quick review of how to take these antiderivatives. So we have negative x and negative 3. My antiderivative is going to be negative x and negative 2 divided by the new power, x squared over 2 minus x. And don't forget, because this is an indefinite integral, you have a plus c at the back here. Clean up a bit, you will get 1 over 2x squared plus x squared over 2 minus x plus c as your final answer for your antiderivative. When your problem is presented like number 2 here, I would strongly recommend to rewrite it first as x to 1/3 power plus x to negative 1/3 power, and then dx. Then taking the antiderivative will be a little bit easier, so you use power rule straightforwardly. You have x to 4/3. Keeping in mind that when you're dividing by the fraction, you're really taking it as a reciprocal, so it's 3 over 4 in the front here. Same thing with the next value. You have x to 2/3 multiplied by the reciprocal, 3 over 2, and don't forget your plus c. It is okay to leave it as 2 separate fractions here, because if we're going to do more with it, then we will do some manipulation with the fractions. Okay. All right, so this is what we're talking about when you have coefficients, right? So in this case, the very first one, the coefficients in the front. When the coefficients in the front, it is multiplied to the integral, to the derivative. So it really just stays there because you're just multiplying by that coefficient. So this would be negative 3 cosine of x, because the antiderivative of sine is cosine of x. Okay, next piece, you have minus. You have sine x here. So again, the antiderivative of sine x is negative cosine x, so positive cosine of 3x. And this is where the chain rule comes in. There's a 3 as a coefficient of the x within the sine argument. Therefore, when you take the antiderivative, things come out as either dividing by 3 or a 1/3. It's a reciprocal. Okay, and you have your plus c. And that will be your final answer. Don't forget, when we are solving for initial value problems, what we're really doing is we're trying to solve for the original equation. So given the derivative, you need to take the antiderivative to go back to the original function. So first thing you should be doing is to take the antiderivative by separation of variables. So separate your x's and y's. Here you have dy equals x and negative 2 plus x, and the whole thing dx, right? Because you separate the x's and y's. Now, to get rid of them, you take the antiderivative, which is the integral, and you will get y equals x and negative 1 over negative 1 plus x squared over 2 plus c. Now, don't forget your initial values. You know that when x equals 2, your y equals 1. So plug in the 1, plug in the 2. Now I'm going to rewrite this so it's a little bit easier to work with. So plug in the 2. I get 2's in here, and hence your equation now becomes 1 equals negative 1/2 plus 4/2 plus c. So you get 3/2 plus c. C equals negative 1/2. Don't forget to put it back in. It is never okay to write your answer like c equals, because you're solving for the equation. So y equals negative 1 over x plus x squared over 2 minus 1/2 will be your final answer for this equation. Okay. All right, trig functions work the exact same way. So separate my variables. dy equals cosine of x plus sine x. Your dx over here. Take the antiderivative. So you get y equals integral cosine of sine, so sine x minus cosine x plus c. put in your initial values here. So 1, and then your pi, so where x's go. So you get 1 equals sine of pi minus cosine of pi plus c. So 1 equals 0 minus -1 plus c. 1 equals 1 plus c. Hence, in this case, c equals 0. Very nicely, goes away. So your final answer is y equals sine of x minus cosine x, and be done. Okay, all right. So next thing is kind of a new thing. This is called a slope field. What slope field is that you are given this derivative, and then so at every single coordinate point, you plug in your coordinate into this formula for your derivative, and you try to kind of guesstimate what your slope would look like. So what typically happens is that we will give you a coordinate like so. Limited numbers, right? You're not going to be given a whole field like you saw in the examples there, but it will give you points like this and say, all right, given the slope, what could the slope field be? So you actually take each coordinate. You take this point right here, that's 1, 1, and plug it into your slope. So let's say your slope, and let's try the first one. The slope is x minus y. Okay, so what does that look like? My slope is x minus y. At 1, 1, 1 minus 1 gives me 0. So that slope is 0. That's a slope 0. That's a flat line, right? Okay, let's pick. So usually we go in a very nice orderly manner. We go with each of the points. So this is -2, 0. So -2, 0 is -2 minus 0. That's a -2. A -2 slope is going to slant left, but it's going to be steeper. So it's going to look something like this, right? A little steeper than -1. So same thing, the next point here is -1, 0. So -1 minus 0 is -1. So it's going to be a flatter line like so. This point is 0, 0. So it's going to be 0, 0 like this. Okay. And then the next point here at 1, 0, you have 1 minus 0 is 1. So this is a +1 slope like this. 1 and -1 are, and zeros are, in my opinion, the easiest slope to graph because 1 is a +45 degree and -1 is a -45 degree. Right? So it's one or the other. And then you have your point here at 2, 0. So the slope is +2, so it's a little bit steeper than before. Okay. All right, let's finish this up because then we can use that to kind of help us see what the other coordinates, what the other slopes are. And you can use this to kind of guesstimate your slope field. All right, I have this point here at 2, 1. So 2 on my formula, my derivative is x minus y. 2 minus 1 is 1, so this is a +1. So these are the same. So as you can see, I already sense a pattern that, oh, all my diagonals, this diagonal is going to be the same, this diagonal is going to be the same, this diagonal is going to be the same, right? And I can prove that one more if I pick another point. So this point right here is going to be 2, 2. 2, 2, 2 minus 2 is 0, so that's a 0 slope right here. So then I can pretty assured that this is going to be a -1, -1 is a -2, -2 is probably -3, -3, -4. Okay, pretty good. So now I have a pretty good idea what my slope field should look like, right? So using that to kind of look at, ooh, what do I have here? Well, I know the diagonals this way are all going to be the same. So the diagonals looking the same. This right here, notice how it's not the same. So I know automatically that's out of my picture. That's not a choice for me. Okay, this diagonal looks the same. This diagonal looks the same. This diagonal looks the same. Okay, this is looking promising. Part C, this is looking, nope, not the same here now. It's not the same when we go down here. So nope, this is not right. And this diagonal right here does not look the same. So my only choice now is B as my answer. Okay. And that's kind of how you do slope fields. There are other ways, of course. Some are a little bit quicker than other, right? So for example, I'm going to pick a different one, right? So no, let's go back to number 7 here. Number 7, your slope is x times y. So it's going to looking at the behavior of x multiplied with y, right? So again, I start with very simple 1, 2, 1, 2, and these are just kind of the basic dots. I didn't do too much in the negative coordinates, but you can definitely do so, right? So my derivative is x times y. Okay, first one is if I multiply by, if any of my x's are zeros, then my slope is going to be 0. So on my x-axis and my y-axis, my slope is 0. Okay, that's pretty good. Okay, here at this point, 1, 1. 1 times 1 is a +1. -1, this point is -1, 1, so it's going to be a -1, right? So, right? This point here is 2, 1. 2 times 1 is 2, so it's a little steeper. This is going to be -2. This point here is 1, 2. Same thing, it's going to be 2, so it's steeper. So steeper 2, steeper 2. This point is 2, 2. 2, 2 is even steeper, so it's going to be steeper like this, looking like a 4. Okay, so again, looking at this graph, I need the two sides to it's going to get steeper and steeper going up, steeper and steeper going up. So the only options are D and A, because this part right here looks very similar to this piece right here. But the only one that's getting steeper and steeper would be D. So my answer is going to be matching to graph D. Okay. Okay. Now I have two leftovers. So let's see. I have A and C. Which one is which? So now I can use a little bit of a shortcut in a way to help me see which one is which slope, right? This one you have x divided by y. So when x equals 0 on top, I get a flat line for my derivative. So when is x equals 0? Along the y-axis. So it looks like along the y-axis, I have zeros right here, looking pretty good. And here I see nothing. So I'm pretty sure my bet is A, right? And then same thing if I look at the other one, when when y equals 0, I get a flat line. So that's along the x-axis. So that's why you don't see them here. Whereas here it looks like along the x-axis, it looks like it's going to be more vertical. So then that's how I know this is option A. This is option C. Okay, you can definitely do more points to see if your assumption is correct. And again, I believe if you do more, the graphs will really show you what the slope field will look like. The more points you do, the more you're going to match what I have here in the options here. Okay. All right. Last but not least, because the slope field is showing me all the possible graph that has this derivative, keep in mind that there's always that constant, right? We can always add a plus C somewhere. So that plus C is what's giving me all these possibilities out there. So that's why you have all these little slope fields giving you the overall picture. So what happens when I give you a particular solution saying that my line must go through this point 3, 2? Where is 3, 2? 3, 2 is right around here. You can look at each line kind of as 1. So it's 1, 2, 3, and then 1, 2. So that's your 3, 2. Okay, so once you've identified 3, 2, you can figure out what your graph would possibly look like. So what I usually do is I ask students to look at this kind of like the current in the ocean and see how the fish will be swimming, right? So if I were this fish right here, 3, 2, if I follow the current, you will see my graph going something like this, kind of like a hyperbola or a parabola, right? In part B, because I chose this point is actually very interesting. It is a straight line like so because of the way that point is on 3, 2. If I choose a different point, my graph is going to look really different, kind of going up like this, kind of like almost an exponential logarithmic function. Okay, and then for this one, because there's no slope here, slope is undefined there, so we cannot cross that point, we cannot cross that section of the graph when we're graphing my line. So my line is actually really one-sided. It's looking something like this when I follow the slope of the rest of the slope field. Okay, and then last but not least, this last point here is going to follow the slope going this way, going this way. So this one's looking more like a parabola. Okay, all right, again, look through these and really practice how the slope fields work. And that's it.